Okay, that seems to work. Perfect. Then let me also, as a backup, do the recording. All right, perfect. So yeah, welcome everyone to today's seminar. And it's my great pleasure to introduce Aiden Abadi, who is actually like here for the second time in a very short time. So that's nice. So Aiden is a researcher at UCL who is working with Stephen Murdoch. And today he will present one of his latest works, which is called Polynomial Representation is Tricky, Maliciously Secure Private Set Intersection Revisited. So Aiden, please, the floor is yours.
Thank you. Thank you. Hi, everyone. I hope you are well. So in this presentation, I'm going to briefly talk about one of our recent works, which explains a set of attacks that can be applied to 3 protocols for private set intersection, or PSI for short. It's a joint work with Stephen Murdoch from UCL and Thomas Zacharias from the University of Edinburgh. So what is PSI? A PSI, private set intersection, is a cryptographic protocol. Its goal is to let parties share their sensitive data in a privacy-preserving manner. I explain what I mean by that. It computes the intersection of sets, where each set is sensitive, is private, and it is contributed by a party. So in this setting, we have got different parties. They do not trust each other, and they have sensitive set of values, set of elements. They want to compute the intersection of their sets while preserving the privacy of their inputs. The first PSI was proposed in around, I think, 2004 by Friedman. And one of the key researchers in this area, most of you may already know him, is Emilian. He has contributed a lot to this area as well. Right, so let's ignore the privacy for a moment and see what set intersection means. Okay. So if you have 2 sets owned by 2 different parties, here Alice and Bob, then the intersection of 2 sets, set A and set B, is a new set containing all elements of A that are in set B as well. So in this example, you can see that the intersection of 2 sets are elements 1 and 3. In other words, the intersection of these 2 sets, or in general sets, are the elements common in both sets. It doesn't have to be 2 sets, but for simplicity, I just give 2 sets as an example. Now let's take the privacy into account as well. So a common definition of PSI is as follows. PSI lets mutually distrusted parties compute the intersection of their private set such that nothing about the set's elements beyond the result, where the result is the intersection, is revealed to the parties. This should hold during the computation and after the computation of this. So, as I mentioned earlier, by mutually distrusted parties, I mean the parties do not trust each other because the other party may act maliciously or may be a bad actor. So it tries to do anything depending on the security model to learn some information about its counterparty elements. So let's get back to our previous example. If Alice is corrupt in previous example, then it might want to learn elements of Bob's sets, which are not in the intersection. Likewise, if Bob is corrupt or malicious, it may want to learn also other elements of Alice's set, which is not in the intersection. So, based on our definition of PSI, and if we put this definition in this example, then during and after the intersection, Alice should not be able to learn 4, 5, 9. Bob should not be able to learn 2. It's simple. Right. Privacy is the most basic property of a PSI. In general, in cryptography, there are 2 types of adversaries: active one and passive one. Passive or semi-honest is the weakest adversary, and active or malicious is the strongest. Of course, there are some adversaries in between, like covert or rational, but for the sake of simplicity, I'll ignore it in this presentation. A PSI that has been designed to remain secure against passive, the weakest adversary, should satisfy only privacy. But a PSI that is designed to be secure against active adversary, malicious one, must ensure privacy and correctness of the results. So in this security model, in the active one, the adversary deviates from the protocol instruction. It does everything to affect the results correctness, and it tries to learn more information than the than honest party would learn. Okay, whereas in passive adversary, the adversary does nothing. It doesn't deviate from the protocol. It follows the protocol, but it observes and tries to learn information. Right. A PSI is usually an interactive protocol. Parties interact with each other over possibly multiple rounds. PSI can be very complicated if we want to take efficiency into account. This is not just for PSI protocol. This is usually the case when we are designing cryptographic protocols. If we want to simplify everything, usually it's not efficient, but it is simple. Simplicity is good sometimes because we can analyze the security of that. But if we want to improve the efficiency, we have to usually add complexity to the protocols as well. So one may ask, why isn't it trivial to design a protocol that generates the intersection of 2 sets? So In other words, why isn't it easy to compute the intersection? According to our previous example, it was easy. You have two sets, we want just elements in common. So the answer to this question is that, first, for one reason, we don't want to use a trusted third party. If we had such a party, then each set owners could send their set elements in plain text or over a secure channel to this trusted party. This trusted party could compute the intersection because he has got everything in plain text. It needs to compare and find the elements in common and send the results to the parties. However, we do not want to use this setting. The second reason why PSI design is not trivial is that these parties do not know the elements of their counterparties. If they knew that, they wouldn't need to run PSI in the first place. Therefore, designing PSI is not trivial. Right. PSI has got various applications. For instance, in online gaming, recently in COVID-19 contact tracing, and again, one of the recent application is in Apple solution, where Apple wants to combat child sexual abuse material. Right. At Eurocrypt 2019, Ghosh and Nilges proposed 3 PSIs in a paper, namely two-party PSI, multi-party PSI, and threshold multi-party PSI. Here, by multi-party, I mean more than 2 parties. So more than 2 parties can participate in PSI protocol. The multi-party PSI protocol is one of the most efficient multi-party PSIs that has been designed so far. These 3 protocols were supposed to remain secure against active adversary, the strongest one. These 3 protocols are quite efficient. They are mainly based on efficient symmetric encryption. They use polynomial representation of sets. I'm going to explain what it means. And they don't use any kind of public key operation or primitives, such as zero-knowledge proofs that are usually used in secure multi-party computation protocols in the setting where we have got active adversaries. These 3 protocols have been proven secure in a strong security model called universal composability, or UC. Because of all these interesting features, this paper has been accepted at Eurocrypt 2019, which is a decent conference. However, we identified serious issues in these 3 PSI protocols. We showed that these PSIs are susceptible to 3 main attacks. So I'm going to briefly talk about these 3 attacks now, then I'm going to explain each attack in more detail. Attack 1, the adversary can learn correct results without letting its counterparty learn the correct result. So it makes its counterparty, the victim, believe that there's no element in the intersection. In attack 2, the adversary can learn an element about the victim's set beyond the intersection. And in attack 3, it can delete multiple elements from its victim's input. This attack can also allow the adversary to learn multiple elements of its victim's set. Now I'm going to briefly explain each attack. Just as a side note, for the sake of simplicity, I'll explain the attack for the two-party PSI, but these attacks can be applied to the other two protocols as well. In attack 1, the adversary, as I mentioned, can learn the actual intersection of the sets, so it can learn the correct results. However, it can make its counterparty believe that there's no element in the intersection. It can do that, and it can easily escape from being detected. So this attack can affect the correctness of the protocol, the PSI. So the question is, what does make attack 1 possible? There's a flaw in the PSI's design. The flaw is that the protocol allows each party to include the product of two polynomials in the final result, where this product, the product of two polynomials, is never randomized by the other party. The attacker can exploit this flaw to carry out its attack. So before I explain this attack in more detail, I need to give a brief background on the use of polynomial in PSI protocols. The idea of representing a set by a polynomial was proposed by Friedman in 2004. This is the first PSI paper. In this representation, a polynomial is constructed in a way that its roots are the elements of the set. It is simple to construct such a polynomial. In this slide, P of X is a polynomial of such a structure. So SI is elements of the set. So as you can see, after we construct the polynomial this way, then the roots of P, polynomial P, are the elements of the set. Also, another observation made by Kistner later on in later paper, Kistner showed that if we have two polynomials, P, A, P, B, where each polynomial represents a set, then if we multiply each polynomial by a random polynomial, and then we sum the results, here in this slide, phi is the result. This phi, this result, reveals nothing beyond the intersection of the sets. So if you give this phi to an adversary, it cannot learn anything beyond the intersection of the sets. Of course, it needs to extract the elements. So it needs to extract the roots of this polynomial, which is allowed, but it cannot learn anything other than that. Okay, so let's get back to our attack 1. Let's have a look at a part of the two-party PSI protocol in the paper in question. So what you can see in the slide is a part of the original two-party PSI protocol. So here in PSI computation, there are two parties want to find the intersection, find the final result. Here, I'm assuming party B is malicious. So in step one, each party is set as a polynomial, then they interact with each other to randomize their original polynomial. However, in step E, 1E, party B, which I'm assuming is malicious, can inject a malformed input into the result, the final result. So as you can see, in the original protocol, this party is allowed to compute PB, where PB is the representation of its original set, multiplied by a random polynomial, R prime B. However, and this remains in the result. So this P cap is sent to the other party. However, the malicious party B can deviate from this protocol. Instead of this product underlined, it can replace it with a random polynomial. Here, I'm calling this R double prime B. So we don't have PB included in that R prime B. So it's just pure random polynomial. Okay. That is the only thing it needs to do to affect the correctness of the result. Okay. Now, what it needs to do, there's another phase in the protocol that checks the correctness of the results. Okay, we usually have it in any secure multi-party computation in the active adversary model. So parties want to make sure that their counterparty has done its part honestly. Right? So now we are moving to that phase. So what you can see now is the output verification. So in the previous slide, I showed you how it can affect the correctness of the result, but it needs to escape from being detected as well. If it's not detected, then it won't be counted as an attack. We call it attack if it can detect from being detected. So it needs to escape from being detected. So what it needs to do here is this simple. When it generates a set of values in a step B, who party B. But the only thing it needs to do in order to escape from being detected is to generate another value instead of delta B. So it sets delta B instead of setting to R prime B evaluated. So this is a polynomial evaluated at Z. It replaces it with evaluation of R double prime ZB multiplied by a new value. This value is the evaluation of the original polynomial PB evaluated at Z, and then it computes the multiplicative inverse of this polynomial. Then it multiplies these two and sets the delta B as this value. So in short, it needs to only set a value, which is here delta B, to a new value compared to original protocol. And if it does so and sends all the values to party A, then party A follows the protocol because party A is honest and it cannot detect anything. So it can simply, party B can escape from being detected.
Can I ask a quick question?
Of course, sure.
How is the inverse of the polynomial specified here? How do you do that here?
Sure. So, good question. So I have skipped some part. All the polynomials, when they are represented, are defined over a final field.
Okay. Yeah.
Therefore, we have always have multiplicative inverse of evaluation of polynomial on something, or we have got the multiplicative inverse is always different.
Okay. Okay.
So what is the consequence of attack 1? As a result of this attack, the malicious party, in our example, party B, can generate correct result for itself. So if it follows the protocol honestly for itself, it can find the correct result for itself. It doesn't need to send the correct result to honest party, but if it follows our attack, it can fool the victim. So the victim can, after extracting the root of the result polynomial, what it sees is empty value in the, or empty roots in the. So by empty roots, I need to say something. So usually the roots are encoded somehow. So we can distinguish valid roots from error roots. So when the adversary attack the protocol, then the honest party cannot extract any value, cannot see any valid roots. By that, I mean empty result. It can see some random values, but those random values are not defined in the protocol. So you may ask why the honest party cannot see the results. Usually, when we have a well-structured polynomial that has certain roots, then if we add it with a random polynomial, the result usually does not contain the elements, the roots of this valid polynomial with a high probability. Therefore, the honest party cannot extract valid roots of polynomial and cannot find the valid result. And this attack can be done successfully with an overwhelming probability. So the problem, this problem, was undetected in protocol's security proof because the proof didn't consider some cases. In particular, it did not capture the case where the evaluation of random polynomial at specific point Z is not delta B, because in our example, the random polynomial can be changed. And then everything can be affected. Also, there was a problem with the proof in general. The proof tried to consider all the attacks case by case, even though it was using a simulation-based proof. It was considering each attack case by case. Therefore, you usually cannot enumerate all possible attacks and you miss it, and this is what happened here as well. So if we put it in the UC context, in the proof, the simulator can distinguish, because of this flaw, can distinguish the real world from either world, which shouldn't have happened if we had correct proof or correct protocol. So this attack can be mitigated if each party randomizes its input polynomial, each party re-randomizes its counterparty's input polynomial, and the result contains only sum of re-randomized polynomial, the addition of re-randomized polynomials. However, and this may add some cost to the protocol, the original protocol. The cost is not significant for the two-party PSI, but it is huge for, or relatively huge for multi-party PSI, because each party needs to interact with the other party and re-randomize its counterparty's input polynomial. Therefore, it adds computation and communication costs to the multi-party PSI protocol. So let's move on to attack 2. In this attack, a malicious party in the PSI exploits a flaw in the sub-protocol used by the PSI. I'll explain what sub-protocol is and why it is used. The adversary can exploit this flaw to check whether certain elements exist or not in its honest parties sets. And this element is not necessarily in the adversary's input set. Therefore, this attack can violate the protocol's privacy, because the adversary can learn an element beyond the intersection. So, as I mentioned, the source of issue is a flaw in the subprotocol. The subprotocol is called oblivious polynomial addition, or OPA. In the OPA, a sender is given the ability to independently pick a random value. And this is problematic because it can pick any value it wants and it can check whether its counterparty has got this value in its input set. So the adversary can see the result of this attack before the protocol, the PSI protocol, is completed. So it has got at least 2 options. It can carry on the protocol and finishes, or it can halt after it learns it successfully carries out its attack. So in case 1, the adversary learns the intersection and finds whether the element it guessed is in its counterparty's set. In the second one, it learns only that element without learning the results. Okay. In the first one, the victim can also learn the intersection. In the second one, the victim cannot learn the intersection. So in the second case, where the adversary halts you can save some cost as well, communication and computation costs, because it doesn't need to take all the steps in order to complete the protocol. So in either case, that the successful adversary learns more than its counterparty does. The probability that this attack succeeds depends on the honest party's set cardinality and the size of universe over which all the elements are defined. So this attack is feasible, attack 2, if the size of the universe is medium or small. But more formally, when the size of this universe is polynomial or constant in the security parameter. In this cases, the adversary can succeed with a non-negligible probability. So, as we saw in the description of attack 1, there's some consistency check. Phase 2, if you remember, that each party checks the other party's input and make sure that it has been well formed and the party has acted honestly. However, in this phase, for attack 2, the proof of the security did not analyze the misbehavior of the adversary in this consistency check. So this phase has been left out of the protocol analysis and proof. So the proof was incomplete. And the adversary could misbehave in the verification. The attack can be prevented, attack 2, if we let parties in the OPA, in the sub-protocol, to run a coin tossing protocol, secure against active adversary, to compute the random value. So in this case, each party cannot pick this random value independently. They need to interact with each other to come up with a random value. If they do it this way, then the protocol, the original protocol, remains secure. And it doesn't impose much cost, additional cost to the original protocol if they use this mitigation. Now moving on to attack 3. In this attack, the adversary can delete certain elements of its victim input, and it can learn whether these elements are in its honest party's set elements. So it can affect both correctness, because it has deleted certain elements, and privacy, because it can learn whether those elements are in the victim's set. So the main source of the issue is that the parties use certain polynomial representation of sets. Specifically, the protocol requires the parties in the sub-protocol OPA represent their polynomial in points value representation, or X and Y coordinate representation. However, if they use this representation of polynomial, then malicious party can affect its victim's inputs by relying on the theorem I stated in the slide. So informally, if we have set of Y coordinates, we can multiply this set of coordinates with another set of coordinates, such that if we interpolate a polynomial of using the product and x coordinates, then the result will miss certain roots of the original polynomial. By original polynomial, I mean the polynomial interpolated from the original y coordinates. If we use this theorem, then if the adversary uses it, then it can affect the results. So it can remove some roots from honest parties' inputs. So the adversary can delete multiple elements of its counterpart as long as it can guess these elements correctly. Also, as I mentioned, if it manages to do that, you can conclude that these elements are in the honest parties set inputs. So it can learn these elements as well. So correctness and price are affected. So in this attack, the adversary can delete multiple elements of its victim elements with non-negligible probability. Again, here in this slide, k elements can delete it. If, again, this the universe of elements are medium or small. I've already defined what I mean by medium or small. So this attack is feasible or non-negligible if the universe of sets are medium, size of it is medium or small. So the main two flaws in the proof that led to attack 3 remain undetected are as follows. In the OPS proof, the definition of malformed input has been limited only to 2 cases. So they assume an input is malformed if the polynomial is of incorrect degree. They have defined what the degree means, correct degree means, and if the input polynomial is z. We showed that the input can be malformed without satisfying either of these conditions. Also, they assume that the only way the adversary can change an original value is via addition. So if I add one arbitrary value with the original one, then I can change it as an adversary. However, it is not always the case because we have got multiplication. So this multiplication has been left out of the proof. They didn't consider this case at all. So how to mitigate attack 3? So simple approach is to use polynomial in coefficient form. In this case, no matter how the adversary can construct its polynomial, then it cannot carry out the previous attack. But this increases the computation cost from O m log m, where m is the set cardinality, to O m to the power of 2. And as you can see, as you know, the gap between these two complexity increases, or the actual concrete value increases when the set cardinality is huge or relatively huge. So this mitigation does affect the performance. To conclude, in all these 3 attacks, an adversary exploits 2 features of the protocol design. One is the polynomial representation of sets. The other one is polynomial-based consistency check during that second phase I explained. These three attacks that I explained, shows us that we need to be very careful when we use polynomials representation in the setting where the protocols need to be secure against active adversaries. So it doesn't have to be PSI protocol. Polynomial representation have been used in many other secure multi-party computations, such as, or other cryptographic protocols, such as secret sharing, such as e-voting, so on and so forth. So we need to be very careful when we use this representation when we are dealing with active adversaries. As I mentioned, all these three attacks can be applied to all the three protocols: two-party, multi-party, and threshold multi-party pieces. And finally, as I mentioned, this was a joint work with Stephen Murdoch and Thomas Zacharias. Our paper appeared at EasyX this year, and you can access it via the link or the QR code. And finally, these are the references, and that's it.
Okay, yeah, thanks. Very nice presentation. Let me stop the recording and the stream, and then we can go over to the Q&A session.
Sure.